Good morning, everyone, and I would like to give you a very warm welcome to come to this morning's seminars. Today we are very honored to have a distinguished guest from Germany to visit us to give a talk on atmospheric chemistry. And before his presentations, I would like to briefly introduce you Professor Andreas Wahner from the ICG Institute. Professor Wahner is the director of the ICG Institute, and he specializes in reaction analysis and photochemistry and the reaction of the atmosphere. So we are very honored to have him with us this morning. So let's give us a warm welcome to Professor Wahner for his presentations. Let's welcome Professor.
Thank you very much, Dean, for inviting me here at the university and giving me the chance to show you part of the research which has been done in the institute. And the title of my talk is Simulation and Field Experiments for Data for Atmospheric Environmental and Climate Research. So it is a part of the research we've been doing in the Institute, ICG2, Troposphere, and the name says that we're dealing mostly with processes in the lower 10 kilometers of the atmosphere. So that's the troposphere. And I will report, I will use data from a campaign. We did a measuring campaign in mainland China, where quite a few number of co-workers in the institutes were involved, and in cooperation with Peking University, and also in cooperation with Academia Sinica, Taiwan, with Professor Xiaoshen Liu. And this campaign was also in cooperation with Tokyo University, and there with a group of Yutaka Kondo. In the second part of my talk, I will tell you a little bit about aerosol processes which have been investigated in the Institute in Jülich, mainly under the supervision of Astrid Kindler-Schaar and Thomas Mendel. But there were also quite a few people involved. So the question is, I want to a little bit talk to you about is what happens actually to organic trace gases in the atmosphere. What is the atmospheric oxidative turnover? Do we understand it quantitative? And what happens then with the partly oxidized compounds in the atmosphere? Do they form, or to what extent do they form secondary organic aerosol? All these questions are most relevant to the climate processes. But in case, what do we know about organic trace gases? Where do they come from? And here is a scheme actually published by Jürgen Kesselmeier from the Max Planck Institute in Mainz. And there he shows where the major sources or emission sources for organic trace gases in the atmospheres are. And you see the largest number you see here, over 10,000, and that's in units, million tons per year, is the biogenic emissions globally seen, which has a big variety of compounds. There are isoprene, but there are the whole bunch of terpenes and sesquiterpenes, but also alkanes, alkenes, and partly oxidized compounds like aldehydes and also alcohols. But this is the largest number. Then you compare that what's anthropogenic sources, estimated global anthropogenic sources from fossil fuel use, like from industrial processes, from painting, whatever you have. There is an estimate that it's about only 10% or maybe 20% of this source. So it's much smaller, but the compounds are quite different. There you have also benzenes or xylenes as emission sources. And the other important source is definitely biomass burning, and it's estimated to be 7 to 40 million tons per year. Sorry, pretty warm. And then you have smaller sources which are coming from the oceans, and there you have mainly alkanes and alkenes, which are by biological processes in the ocean then emitted to the atmosphere. But all these organic material, they are degraded and oxidized by atmospheric processes, by oxidation schemes, and part of those they produce then ozone, or in extreme events photosmog, but also they produce or they contribute to the production of particles. And here again, how important this is for climate issues is shown in this diagram, which shows you a measure, the radiative forcing, which is a measure of the efficiency of several gases, changes of these gases between pre-industrial times and 2005 to global warming. And they can be translated in temperature increases. But here on this scale you directly can compare what the change of these emissions, or the concentration, more better clearly said, concentrations in the atmosphere contributed. And the largest single compound which contributes to global warming, red is warming, is carbon dioxide, and that has increased due to the growing use of fossil fuels. But you see all the other compounds, or most of the other compounds like methane or N2O and ozone, where ozone is not emitted, but it's formed in the atmosphere, are also of pretty much importance for global warming and for the change of the temperature. And you see, ozone is not emitted. Ozone is formed actually by oxidative processes and is a consequence of many other gases. Oh, thank you very much. And you see, methane is a gas which interacts with the trace gas degradation in the atmosphere. So it's degraded in the atmosphere, it's oxidized. CO2 is more or less chemically stable, or it is chemically stable in the atmosphere. Methane not. And as well, as I said, ozone is produced, so it's a result of chemistry, but also the aerosols are, as well as the direct effect and the indirect effect, because aerosol concentration, aerosol chemical and physical properties have an influence for the cloud albedo effect. You can have smaller cloud droplets, you can have larger cloud droplets, depending on what aerosol type you have there, and that has an effect on the reflectivity of these clouds, and therefore leads. Change here is calculated to lead to a cooling. Blue is cooling. And also more aerosols scatter more light back in the universe, so it is actually also a cooling effect net. Though you have also aerosols like soot, which are black, and they absorb radiation, so they have a contribution to heating. But overall, one estimates that all increases in aerosol has more a cooling effect. But you see also that these these cooling effects compensate to a large extent the warming effects of the other gases. And so net, you have about radiative forcing, if you sum up over them, which corresponds in numbers closely to that of CO2. But that's just the reason, because you have cooling effects and warming effects which compensate each other. Important to keep in mind in general is that the time constants, or the lifetime of these substances in the atmosphere, are quite different. CO2 remains in the atmosphere for about 800 to 1,000 years, or even longer, because finally it's deposited in the oceans. But methane has a lifetime of about 9 years before it's oxidized. Ozone of maybe a few weeks, and aerosols of also maybe 1, 2, 3 weeks. So if you stop emissions of those, you will have very quickly a change, and quickly a change of a compensating effect. If you would, for example, reduce the emission of aerosols, and then you would get a much higher activity of radiative forcing of these greenhouse gases. So that's to keep in mind if one does also measurements of reducing the greenhouse effect, that there are different lifetimes. CO2, you can hardly do anything about it. What's in the atmosphere, it's in the atmosphere for a very, very long time. So, but now, coming back to the atmospheric chemistry, and in very simple terms, you can understand atmospheric chemistry or get a glimpse of atmospheric chemistry, that there's essentially one radical or one molecule which does or initiates most of the job. For most chemicals in the atmosphere, they are reduced and they are going to be oxidized. Mainly because the atmosphere contains 20% or 21% oxygen, but it's not reacting directly. So you need a type of catalyst, a very active species, which does the initial step of oxidation. And that is actually, for the troposphere, the OH radical. The OH radical is very much reactive, it's a radical, and it reacts with most of the emissions. But it's also very much active and very much active and oxidizing, because it's getting recycled. Because during each oxidation, for example, of CO or methane or volatile organic compounds, which is a whole group of the organic carbon-containing compounds, they all get attacked by oxygen, by OH, and then in subsequent reactions there is formed the HO2 radical or RO2, which means that you have a peroxy radical of the organic compound. And these get recycled to reform OH. So you have a catalytic recycling of the radicals, and that makes it also very efficient. First, the high reactivity. Second, the recycling of the OH radical. And this recycling is done in most instances, as we understand it, with nitrogen oxide. And there we come to another point. Then this reaction here, HO2 plus NO or RO2 plus NO, gives you NO2, which such form NO2 is then photolyzed, and with oxygen it produces ozone. That is the single source of ozone in the atmosphere. So important is then the lifetime, and you see here, if we want to understand the system, then we need to measure mostly those, and test the system. We would like to have also the turnover rates, because what is lost here, or what is used up here for oxidation, should return here, except what's forming H2O2 or what is reacting with NO2. That's the way OH leaves the system for HNO3, for this, forming this acid, and produced it as originally by photolysis of ozone. So you actually, to test if our understanding of the oxidation scheme is complete, or if we have a realistic understanding or quantitative understanding, then you need to characterize all these errors, which are turnover rates. And we concentrate at the moment on these turnover rate, so the measurement, because this is a whole variety of VOCs, of OH, with all these VOCs, what is the turnover rate, and that this is determined actually over the lifetime, so of OH. And we did this in a field campaign in China, in the Pearl River Delta region, which is shown as a map here. And this study was a study altogether of the emissions and the processing of the gaseous pollutants and aerosols. And also it was the goal to develop strategies for air pollution control, and with the partners I mentioned already in the beginning. So what we did there, we did a kind of lifetime measurements, And this apparatus works in principle the way that you flow in outside air, you have a laser beam, a short pulse of a laser beam at a UV wavelength and through the whole volume of this flow tube, and this suddenly produces OH radicals. And then the air is flowing after this laser pulse. You produce everywhere OH radicals. The OH radicals are reacting with all the substances which they can react to in the outside air, which is drawn in here, and slowly it's the air moving along the flow tube. And at one position there, you take a sample of this air and detect the OH radicals in this by laser-induced fluorescence apparatus. And so you get a time profile over this airflow after initiating a whole OH concentration. And so you call this a UV pump and LEF probe technique. And what you get actually is OH decay curves over a certain time, and this flow essentially determines the lifetime of OH in this tube. So, and the lifetime is mainly determined by all the reactions of OH with the compounds. So what you measure is the lifetime of OH or the turnover rate I showed in the previous graphs. And if you look at the results, then you find this blue curve. This is averaged over about 15, 16 days of measurements during this campaign. And so it's an average diurnal profile of the OH reactivity or OH lifetime measured in outside air in the Pearl River Delta. And now you see that during the night you have higher reactivity. That means you have emissions on concentrations which are not degraded by OH. During nighttime you hardly have any OH, and so pollutants get not deoxidized, not degraded, they accumulate, and so you have higher reactivity, potential reactivity. During daytime you have OH, you actually have also a higher boundary layer, a higher mixing height, you have lower concentrations, but maybe also more emissions. So the sum of it, of the reactive compounds, are shown, are actually reproduced in this total reactivity measurement during the day. But still, you get pretty high reactivities of about 20 per second. If you compare that with clean air situations, then you would get 1 per second or less. If you have a, well, not urban, but rural, normal rural situation, you can expect to have lifetimes between maybe 5 and 12 per second. So 20 per second is pretty high. It indicates you a high reactivity, a high photochemically processing state of the atmosphere. So you have a lot of pollutants, you have a lot of OH probably, and you process a lot. But now you want to understand this measurement, and so during this campaign also a whole range of VOCs were measured. NOx, which also, or is also reacting with OH. NO2 is reacting, so you calculate this, and CO as a major contributor for the reaction with O. These all were measured, and then you can calculate with the known rate constant and the measured concentration what should be the reactivity with OH. And if you do this and add all these contributions up from the measured species, you end up with a black curve. And what you easily see, there is about a factor of 2 missing. So you would assume that you haven't measured all the compounds. And that's true because, I mean, that's again a list of all the compounds measured, so a whole range of VOCs. And, but what you do now, you take a reaction mechanism, for example, RACM, it's a known comprehensive reaction mechanism, and there you calculate with the measured VOCs, let it run, and the reaction produces partly oxygenated products, which again can react with OH, with products. So if you do that, then you get the ones you measured, plus the additional reactivity from partly oxidizing the VOCs. And if you compare or add this up, so it's a staggered plot, then you nearly achieve, again, this is the red one is here, the measured curve of a reactivity, then you nearly achieve mostly the observed reactivity. But that means also, even if you measure a whole bunch of VOCs, then you still miss out on maybe half of the reactivity, half of the chemistry which is going on. Because these intermediate compounds, for example, from isoprene degradation, if isoprene reacts with OH, you get a huge amount of different products or in-between products, which again partly react with OH. And that is then compensated or calculated in chemical reaction mechanisms, and then you get up this curve. But astonishing is that our understanding is, or seems to be in this respect, quite good. So we can at least explain with a model and a whole bunch of measured VOCs what is the turnover OH with VOCs with CO. So from this situation we can assume, okay, that is fairly good understanding, we can reproduce this curve. But now look at the OH measurements we did at the same time. And that's the red curve. It's also the same range of days, averaged the diurnal variation of OH. You see during the night you have hardly any OH, and in the morning it's increasing. Noon to afternoon times you get high OH concentrations, and the sun sets, you get lower OH concentration. This is measured, and then also, as I showed in the beginning, we need the turnover, we need the concentration of OH, and we need the concentration of HO2, which is shown here. This is also a diurnal variation measured. In addition, we need the NO, which is directly measured here, concentration during the day, because then NO is reacting with the HO2 and the RO2s to produce ozone, but also to recycle OH. And the lifetime measurements, which gives you the turnover. So now we have, in principle, quantified the whole, or most of the reaction scheme, especially by the lifetime measurements, because it accounts, as we understand it, for all the turnover of OH. So what happens now if you put these data in a model and let the model calculate with the turnover rates, lifetime measurements, NO measurements, and all the chemistry, and let now the model calculate what our model understanding says, what is the HO2 and the OH concentration. And these are the dashed lines up here. And what you see, the model reproduces quite nicely the HO2 concentration and the diurnal variation of it, but it fails dramatically to produce the OH concentration. So there is a mismatch between the really measured OH concentration and the model reduced OH concentration, and that means that the recycling through NO or other sources of OH are missing. And if you look closer at these curves, then we see, oh, we get actually a pretty good match during the morning hours, maybe till the noon hours, late morning, we get a pretty good match. And if you look at the NO, then it turns out that here, NO in this situation is going after the morning hours at noontime to very low values. By the way, I want to point out, that is the reason, even in polluted situations, you need to have very sensitive NO measurements. You may think that NOx is 10 ppb. Oh, that's an easy measurement. Fine, there are lots of apparatus which can measure 10 ppb, 50 ppb, but pretty good. But what you need for such an analysis, you need not NOx, which is the sum of NO and NO2, but you need a measurement of NO. And you see, even though at this situation NOx was in the range of 10 to 20 ppb, NO in the afternoon was 100 ppt. And not many measurement equipment can do that. I mean, there is available, but you have to take care, and also take care of the calibration. But this is the clue of it, because here you have very low NO concentration, and that determines actually the recycling. And in the model, as we understand it, we have the HO2 measured concentrations times the concentration of NO gives you, times the rate constant, gives you the recycling of OH. And the result of it is that you get this model curve. But observations are much higher. So, as it happens to be, there is a gap, and this points to a gap of understanding. And as we show this in a flow diagram with turnover rates indicated by the arrows, then you see we quantified this path actually, OH and RO2, these two we quantified by the lifetime measurements, so it's red, we measured that essentially, and then we split it up by model calculation. And we quantified by HO2 measurements and the NO concentration this red path. But this is imbalance. The blue arrows show you what is actually missing. What's one solution where you get it in balance. So the blue paths, and also from RO2 then, you need to have these reactions, but it can't be reactions with NO. And also, by the way, HO2, as known, reacts also with ozone. This is also not enough. This is included in this bar, actually, and the model calculates this. So there must be an additional reaction, which is not known so far. And though it's not going through NO, there's also a question how much influence this has for ozone production. Because, as you know, as I showed you, HO2 or RO2 plus NO gives you the NO2, and this photolysis of this NO, so produced NO2 gives you ozone production. And so you have a stark mismatch of this. So further analysis has to show how much influence this has of our understanding for ozone production in the troposphere, and also enhanced trace gas degradation you get, because current models, they don't have that in there. But obviously, and as pointed out, that is observed actually just as at lower NO concentration. So we say amount below 1 or 2 ppb. NO, this seems to happen. And that's also clear because you can run these processes and they don't matter anymore if you have higher NO, because then most of it, then this part would be only 1% or less than that from the turnover. So in the error it would be. So you observe it can happen all the time, but it's not important. But it gets important, these processes, when NO is lower than 2 or 1 or 2 ppb. Okay, so and if that this additional mechanism with the blue arrows work, I could show you in this. There you have a dashed line in there, which is the model with the extended scheme and the OH measurement, and they fit actually pretty good. Even the HO2 model fits, because it has a small influence on HO2, these reactions, they even fit better. So it seems to be that this is at least one solution of the question of the mismatch between measurement and model as we know it, but it points out that our understanding of atmospheric chemistry processes, essential atmospheric chemistry processes, are not complete. So, but I must switch a little, I want to switch a little bit the subject now and go to the theme, what happens now? We see we have produced a lot of partly oxidized trace gases, or actually also acids probably, and what happens to these organic trace gases in the question how much of those may be going to the secondary aerosol, organic aerosol. And for these questions, which is a very complicated but important question also for climate issues, but also for chemistry issues, where do all the organic stuff go, it is important, actually, because it's so complicated, it is the first approach we took actually simulation experiments, so under controlled conditions. But first to show you, well, models always calculate nice pictures, and they may show you, for example, the SOA, the secondary organic aerosol production from anthropogenic sources and biogenic sources. You can turn off some of the code, and then you get these pictures, and there at sense you see that organic is the same color code that in Europe, that's Europe, the biogenic contribution to secondary organic aerosol is much, much higher, especially in these areas where you have large forests and actually also lower temperatures. And this is one result, and this model actually predicts very high biogenic secondary organic production, aerosol production. But if you look at other experiments and look how the models actually work, model results on secondary organic aerosols, if you do that, then you have here from Seinfeld 2004, Chang and Seinfeld from 2002, he uses 14 terpenes with certain rates of solar production and comes up with a global model of about 11 teragrams per year production. Durban, 2003, has a model where he just uses alpha-pinene as a surrogate. And there are some investigations from this alpha-pinene in chambers and in lab work where you can estimate by the oxidation how much secondary aerosol you get. And alpha-pinene is an important biogenic emitted compound. So he comes up with a number of 63, so nearly six times higher global solar production. Kanakidu in 2000 uses alpha and beta pine as surrogate for a whole variety of biogenic compounds, comes up with a similar, even higher number. But then Kanakidu in 2003 uses actually alpha and beta pinene in toluene and xylene and has a variation. It's a two-product model, well, she comes up with a range from 7.4 to 44 teragrams and averages, well, she says about 20. So again, a factor of 5 lower than the previous studies. LAC 2004, also 24 to 15, and Bonn 2004, using alpha-pine says 20. But you see from these just model studies by using some lab work of surrogate compounds, mostly alpha and beta pinene, you could even come up in the model with a big variety. But now I think it's important to test this under more realistic composition. Not only alpha pinene is emitted by the biosphere. So we also can, another step forward is you can see the difference in the model here and measured. If you look at vertical profile of secondary organic aerosol, then black is measured, for example, in ACE Asia, and that is modeled, and you see that's quite a difference. The model doesn't reproduce the observed secondary organic aerosol. And that is also true for other publications with other models here. They underestimate to a great deal the solar production. So we can say even also in the altitude, it's not really possible. Now, the point is, if you want to investigate it, secondary aerosol, it gets quickly very complicated because secondary aerosol is not a chemical compound. It's a huge variety of chemical compounds, and that is somehow indicated here. If you have a composition of an organic aerosol, which is, sampled from the atmosphere, then you have here in micrograms, you have in percentage here, down there is the number in micrograms, then your carbon contents, maybe organic carbon contents, maybe about 30 to 40%. That you find regularly in aerosol. Of these 30 to 40%, you get elemental carbon and organic matter. But there you get from this only 80% in this publication, in this Ghent winter 98 sampled aerosol, as an example, 80% organic matter. Now you want to know what compounds are in there. But now you take these 80% and extracted by different methods, or you have unextracted and not uneluted organic matter, and that is then what you can elute. So you can solve something to put to an analysis, to a chemical analysis, and that's only about nearly 20% of the former 18%. So we are now down here for a whole bar of 40 micrograms. So what you really can analyze are only, or principally can analyze, is only 2.7 micrograms out of the 17 micrograms. And then you can distinguish by chemical analysis that there's about 60, nearly 50-60% acids, and the rest is neutrals. And if you do all this in further analysis, then you can not identify by complicated analysis about 20-30% of this, and what is principally identifiable is this. So it's only what you can say, this is this compound, then it is 0.44 micrograms from these 17. Organic matter 17.8, and what you can say, well, these are these compounds, it is only a very small fraction of it, and there's alkanes, there are fatty acids, there are PAHs, there are lignin or lignite derivatives, and oxygenated degeneration products. So a whole variety even there, and these are thousands, or at least 1,000 compounds, what you can sum up in here, but then you have only analyzed from the organic matter a very small fraction. So you see, it is difficult to now have a reaction and find out for each of these compounds how does it produce, why it is in the aerosol. So we did a different approach. We said, we want to understand how much organic matter is produced by biogenic emissions, because in the beginning I showed this is an important question and one wants to know, but maybe in this stage not to know what are all the different compounds. So we have a simulation experiments where we have a chamber where we grow plants, specific plants, under natural but controlled in a natural but controlled environment, and the air of this is then pumped in a reaction chamber where we can simulate atmospheric oxidation. And what we investigate actually is, in the chamber, is the emissions of a spruce, of a pine, and of a birch, small plants obviously. And these are, at least for Europe, important plants, and we can compare that with a control experiment with alpha-pinene, which is mostly used, as I showed, in model calculations. Now, we can characterize the plant emissions actually by oxygenated VOCs, and in the birch we have about 40% oxygenated VOCs, a whole range, about 20% sesquiterpenes, and about 40% monoterpenes. Alpha-pinene is obviously a compound which is a monoterpene 100%. But real plants have different amounts of these sesquiterpenes and oxygenated VOCs, which is investigated here and is shown principally. So what does it have an effect? What you want to know is how much, during the chemical reactions, how much aerosol is produced. And I show you here the maximum volume during this reaction, oxidation reaction, which is produced, and against how much of the monoterpene and sesquiterpene are used up. So this is then shows you how much it is produced in aerosol volume of secondary organic aerosol. And here's the curve for alpha-pinene. There's just alpha-pinene, make an atmospheric oxidation scheme with a lot of reactions, and you find that you get an onset of aerosol production at about, let's say, 70 ppbc consumed. And the nice thing is you have a linear relationship. The more you consume afterwards, the more aerosol volume you produce. And that is a nice curve, and that is a nice curve also because modelers like these curves. You have two numbers, and then you can produce, you put them in your model, a linear relationship, and then produce the SOA production. So now let's look what happens if you take a real emission from screws. Well, what you see first, you also have a linear relationship. That's good. Seems to be easy, but the second thing, the slope seems to be similar. That's also good, but the onset, how much consumed monitor beams and sesame beams you need is much lower. Now look at pine, emissions from pine, it's even lower. The slope is similar. So you would have in the real atmosphere much earlier, and much more actually also aerosol produced at lower consumed concentrations of the emissions. And even birch is even a tick lower, but maybe similar, only 4 points. So there you see what is used in the model does not, in this indication here, does not represent the real what happening from aerosol production, secondary organic aerosol production with real emissions. And this only single plants. So it seems it depends on the mix. That's the first hunch here, that it depends on the mix, how quickly and by how much reaction you actually produce aerosols. But there have to be experiments. If you mix the emission from birch and pine, then may have additional effects. We don't know yet. But this only shows you that this curve, which is mainly used in models, is not correct, and you would expect that the models, if they take more realistic, a little bit more realistic approaches, that then you would get actually higher aerosol yields. So I come to the summary. Actually, what I showed you is that the tropospheric reaction mechanisms, this seems to describe a turnover with OH radicals fairly good, within, let's say, 20%, using measured OH concentrations and turnover rates. But the second is that the secondary oxygenated trace gases are important to explain these turnover rates. In PRD, what I showed you, it's about 50%, and not the primary only measured VOCs. But also that the OH concentration is at conditions when NO is lower than 1 ppb, maybe a factor of 3 too small in the models in such an environment where you have biogenic emissions and low NO. But so it has to be shown what effect this globally or in other environments have. But this type of environment you find in vast areas, mainly over the Amazon forest, and that is quite important. So an explanation could be that the dominant source for OH, or what we think is a recycling reactions between HO2 and OH, RO2 and OHO2, are missing in the current understanding. And if you look at observations which have been published from other campaigns in other environments, also with low NO, then it seems to be that at least in rural or forested North America, or as I said, in the tropical rainforest, similar conditions exist, and that you have a much faster degradation of hydrocarbons than known before. And to the question, how much formation of secondary aerosols? I mean, it's very hard to do this in field experiments, so we're at the stage to do this in simulation experiments, what I showed you, and there we have a simulation of a plant emission aerosol system, which seems to be necessary, and the first results show that it's promising to enhance the further understanding. What we see is that there seems to be a linear dependence of processed plant emission and aerosol volume, and also what I haven't shown, aerosol formation rate and growth. That is the good news. So it doesn't seem to be that complicated. It could be parameterized. But that oxygenated VOCs and sesquiterpenes are important precursors for the secondary organic aerosol formation, and And also an outcome of this investigation is that the real plant emissions seem to be much more efficient in formation of secondary organic aerosol than alpha-pinene, and so alpha-pinene to be used in the model to explain secondary aerosol seems to be not sufficient as proxy. So we need actually, by more investigations, a better parameterization for the description. Thank you very much.
Thank you very much for your wonderful presentations. Questions from students? Yes.
Dr. Wahner, I noticed in your presentation the OH measurement in the nighttime. I noticed that the concentration of OH radical is in the level of 10 to the 4 or 5th molecules per cm cubic. I think it's much higher than what I learned before. So do you suggest this? And is there any other source or reservoir in the nighttime of OH radical?
That's a very good observation of the plots. So they were clearly enough, I can say. That is true. I mean, let's say even higher than 10 to the 4. It's several times 10 to the 5th observed in average in this environment. And that is also not the first observation of the higher nighttime OH. So OH should be essentially close to 0 during nighttime because there may be HO2 processes by NO3 degradation of ELCs which produce HO2, and then you have a chance to produce OH by reaction with ozone if it's present. But if you calculate in the model, it should be very, very low. So there is other surprises embedded, I must say, in these measurements. And we don't have an explanation yet for that, and we haven't, detailed analyzed these data, what it has to be, but what it could be. But there are more reactions, dark reactions, which produce ozone in this environment, in a high VOC environment with ozone and NOx present. So I can't tell you. We will estimate, the first approach will be to estimate the NO3 contents, the NO5 contents. There are some measurements in this, some indications for measurements in this campaign, and then we have to calculate what consecutive reactions could be. But you see also, if you look closely, that during dawn, actually, it's behind even the reduction of the OH concentration and the sunset. It should actually more or less closely to each other, parallel going. But it's actually, if it's getting down, it's even longer what you expect from the JOCD values, more OH there. So you have also during sunset different processes. In the morning, some very early OH can be explained, seems to be, it has to be proven, but can be explained with additional formation of HONO, nitrous acid, which is much more quickly photolyzed to produce OH than ozone. So there's an indication that that could be in the early morning hours, at least part of it could be. And by the way, also during the night, during daytime, honophotolysis plays a role, but not a major role in this environment. But it's still under, your question is still under investigation. But there is interesting features still. And the fact of it, I have to point this out, and that is also applicable for other measurements, also for Yavos measurements or for other systems we measure. There are two things which are of major importance. First, the data quality and the reliability of data. And I have pointed in this case it out for NO measurements because you can buy equipment, measures NO, NO2, and it's applicable for pollutant ranges. So you have measurement ranges which are wonderful and apply for that. But then you get a situation where even in a polluted, you have very low NO because you have so much ozone and it goes away. And if you had an offset of 1 or 2 ppb there, then you would get to a totally different conclusion. Actually, you couldn't explain it at all. You get a mismatch. So there, these measurements were done with a very high, highly sensitive fluorescence system, which can measure that. But others can do it. So you have to be sure about your correctness and data quality very, very much like, and also in advance. You don't have to think, oh, I measure in a polluted range, so I don't need to be calibration that carefully. I mean, I have large numbers. Sometimes then suddenly it depends on the precise measurement of a low number which just happens and points to you. And the second thing is the completeness of measurements. So that means that you nowadays, to find new explanations or gaps in our understanding, it is quite important that you have precise measurements of many compounds, as many as possible obviously, but they all have to be precise. It doesn't make sense, come back to the first point, to measure all of it, but having half of the measurement not really a good calibration to it. And you better don't do it, then you better do precise measurement of a smaller set, or even as large as you can do precisely. And that is always, I mean, you need the capacity, you need the right equipment, you need the right whatever. So that is the most two important things. It is difficult to have a not complete data or not qualified data set, and then you get to interpretation, and you end up with nothing, though you have put it all away. That also, from this campaign, shows it quite clearly, and we can do these conclusions only because we have the OH, the lifetime reactivity, and the HO2 measurements, which in itself are very complicated, together with precise NO, NOx, and VOC data. So that's the reason also why many other groups were, I mean, not only one group can do this, we need collaboration with partners. Yeah. More questions?
Small questions. I remember in the recent article published in Science, there's a book talking about micromorphs or H2 and O2, the production for the additional OH particles in the data.
Yeah, that is tested in here. It's a very slow process. It's not applicable to here. It's a percentage. No. It's a nice reaction and it's there, but well, it's a new reaction, no one knew before, but it's too small. It's too slow. In this environment, it is.
Can you explain your aerosol model a little more? Because I found that you also have problem of the SOA.
We don't have an aerosol model. I mean, I showed literature values from all these other global models where they have aerosol modules in there. This is parameterized, and as it's in some instances quite easily done. You take from the literature the aerosol production by alpha binding during the oxidation. And at a certain concentration level, then you produce these aerosols. And if you get more complicated, then you have even with the equilibrium pressures, so with the temperature and the pressure and the amount of alpha binding there and sunlight, then you have one line is this, one formula, and you produce so much SOA. That is how simple some models, I mean, and if you have a global model, you can't put a very detailed in there in most cases. But they are more complicated models which have actually several products or several primary emissions, biogenic emissions in there, and they don't have a reaction scheme for them in there. They just connect the concentration, sunlight, humidity maybe, and temperature, and then they say if I have that much, then I have that much aerosol. And the linear the linear observation, or the observation of the linear dependence of the aerosol volume and growth, actually what I haven't shown, that's also linear, seems to indicate that yes, that could be an easy approach. I have a linear relationship by the consumed or emitted then alpha binding, but not alpha binding, but you need the mix, you need more molecules to actually quantify this by these experiments. And I do not claim that from these experiments I've shown we have done so far, you can actually cover the whole thing, but it's a better approach. But you need mixes of different plants, real emissions of different plants. And that seems to have a large effect on how much aerosol you get in the onset, at what concentration, process concentration you get. So that's all I can say. I mean, we don't have made out of these measurements now a new model. We are in contact with modelers to, well, fit this in. these results, but there are more measurements clearly needed under also other conditions. But the message here, the models as compared, I mean, I showed you some measurements in the atmosphere, the models are on the very low side. And these simulation experiments seem to indicate, yes, they are on the low side because they haven't taken into account at all.
Right. If no other more questions, then let's thank you, Professor Wahner, for a very wonderful presentation.